All right, today we're going to zoom way in on the science behind those satellite maps you use all the time. We're going to unpack one single but absolutely critical concept: spatial resolution. It's the secret that really controls what we can and can't see from space. And by the end of this, you'll get it.
I mean, it's a great question, right? It gets right to the heart of what this is all about. How can a little sensor, hundreds of kilometers up in the sky, possibly capture something as small as a car or a single tree? Well, it's not magic, it's physics, and it all starts with a single point of data.
Okay, so let's set the stage. You've got these satellites constantly whipping around the Earth, taking pictures that somehow end up on our screens. But, that journey from way up there to down here isn't perfect. And the quality of those images, it all comes down to the resolution.
At its core, spatial resolution is really just about the limits of a satellite's vision. You can think of it as the finest, tiniest detail the satellite can make out before everything just turns into a big old blur. So how do we actually measure that clarity?
Well, the answer is in the most basic building block of any digital image you've ever seen: the pixel. But when that pixel represents a real patch of Earth, we give it a special, more technical name.
And this is the key metric you got to know: ground sampling distance, or GSD for short. So if a satellite has a 10-meter GSD, it means every single pixel in its image represents a 10 by 10 meter square on the ground. Everything inside that square, a car, a few trees, the corner of a building, it all gets averaged together into one single color, one single data point.
Now, of course, not all satellites are created equal. We group them into these different classes. You've got your coarse resolution, where one pixel can be over 100 meters wide, huge, all the way up to ultra-high, where a single pixel is smaller than 30 centimeters. The range is massive, and each class is built for a completely different job.
This brings us to a really important rule of thumb in this field. See, just because an object, say a 4-meter-long car, technically fits inside a 10-meter pixel, doesn't mean you can see it. In fact, with that satellite, the car is totally invisible. This rule explains exactly why that is.
So to even detect that something is there, to see a little blip on the image that's different from what's around it, the object has to be at least twice the size of one pixel. It has to cover at least 2 pixels for the system to even register it as a thing.
But to identify what that blip is, to actually be able to say, that's a car or that's a building, well, now you need that object to cover at least 5 pixels, and honestly, even more is better. And that is why getting super sharp, identifiable images from space is such a challenge.
But here's the thing. The world isn't made of neat little squares, right? Nature is messy. And when you lay this perfectly clean grid of pixels over the real, complicated world, things get messy, especially at the boundaries.
This brings up a classic problem. So what color does the satellite give to a pixel that's half on a forest and half on a lake? Is it green or is it blue? The answer is kind of neither. And this creates a huge challenge.
What you get is what we call a mixed pixel. The sensor doesn't just pick one. Instead, it averages everything it sees inside that GSD. The signal it sends back is a blend, a mashup of all the light reflecting off of everything in that little square.
But here's where it gets really cool. Scientists can actually work backwards. They can take that one blurry pixel color and, using some really clever math, a process called spectral unmixing, they can figure out that, hey, this 30-meter patch of Earth is actually 60% forest and 40% water. Pretty amazing.
And there's another weird thing that happens. If you have repeating patterns on the ground, like rows of crops or buildings, and they're smaller than what the pixels can clearly see, you get these strange, wavy, almost vibrating patterns. It's an optical illusion called aliasing, and it's a classic giveaway that your resolution just isn't high enough for what you're trying to see. Okay, so if we have all these problems, blurry pixels, optical illusions, how in the world do we get those stunningly sharp satellite maps we're so used to seeing? Well, the engineers and data scientists have a few very clever tricks up their sleeves.
So here are 2 of the most popular methods. Pan sharpening is basically a math trick. Satellites will often take a really sharp black and white picture at the same time as a blurrier color one. This technique just combines the detail from the first one with the color from the second one to make a single, sharp color image. Then there's AI super resolution. This is totally different. This is a prediction, where a machine learning model makes a very educated guess about what the details between the pixels should look like.
But all this brings up a bigger question, right? Why not just build every single satellite with ultra-high resolution and just avoid all these problems? Well, because it turns out that designing a satellite is all about making really, really hard choices, all thanks to the basic laws of physics.
So here's the first huge trade-off. You can build a microscope that sees incredible detail, but only over a tiny, tiny area at a time. Or you can build a wide-angle lens that can see a whole continent in one shot, but it can't make out a single car. You just can't have both in the same sensor. The higher your resolution, the narrower your field of view or swath is going to be.
And the second trade-off is all about time. A high-resolution satellite, it's like a professional photographer. It takes one perfect, gorgeous, detailed shot of a place. But it might take weeks for its orbit to line up again so it can see that exact same spot. A low-resolution satellite, on the other hand, is more like a security camera. It gives you a daily, less detailed glance of the entire planet, every single day.
So this brings us to what's often called the impossible triangle. When you're building a satellite, you have three things you want: sharp detail, frequent visits, and wide coverage. But the laws of optics and orbits mean you can only ever pick two. You always have to sacrifice the third.
Okay, so let's pull all this technical talk back down to earth, back to something we all use, the maps on our phones. All of these details we've been talking about directly affect the kinds of maps we can even make.
You see, there's a direct link between the scale of a map, that little 1 to 50,000 number in the corner, and the satellite resolution you need. That scale tells you the smallest real-world thing it even makes sense to draw on the map. So if you want to reliably map, say, a 1-hectare forest, you absolutely need a satellite from that medium-resolution class, like a Sentinel or a Landsat.
And what this all boils down to is that there is no single best resolution. It's a myth. If your job is to track global weather patterns, a coarse, daily view of the entire planet is exactly what you want. If you're trying to identify a specific car in a parking lot, you need that ultra-high-res stuff. The tool always has to match the question you're trying to answer.
And that leaves us with one last thing to think about. Now that you understand this impossible triangle of choices, if you were the one in charge, what would you build? What would you prioritize? The sharpest possible detail or a constant, watchful eye over our entire world? The choice you make determines what secrets you get to unlock.